Good afternoon. This is Maj Jay Trivedi. We'll give a few more minutes for other people to join, coming from another room to another. This room. Can you hear me loud and clear? Lieutenant?
I can hear you. I'm not so sure.
Okay. Because I cannot see if people are in the room or not right now at this point.
We have 7 attendees in the room right now.
Great, great. Okay. We'll give a few more minutes for others to join.
I have a message from the participant that say they can hear you loud and clear.
Great, thank you very much. All right, so great. So again, probably you are seeing the slide already on the screen. I cannot differentiate at this point, but I'm Maj Jay Trivedi. I have been with CAP since 2003. I joined with Milwaukee Squadron, a Chicago Executive Squadron. It's a composite squadron. And over the years, I have held a number of roles, including the AEO for the squadron and all the way to the master's rating. My interest more lies with aircrew and aviation mission air operations. And I have been AOBD, FRO, current, as well as I have gone through all 3 air schools, NISA, AFRCC, basic inland course, as well as GSAR, which is a National Search and Rescue School. And again, it's been a great interest in those areas. And so when actually we have anything major that comes up, it's kind of helpful to be able to ready and help out. As for some of the other key missions, I had signed up for Texas tornado back in 2017, 2018. And I think 12 hours before we were supposed to be leaving in the morning, we got a call from our wing commander saying that we don't need resources. So that was one of the, I guess, good and bad thing in terms of that, good is that they had plenty of resources, so people were being helped. The bad is we were all pumped up, ready to go, and now you wait, say stand down. But anyway, that's the nature of things we do. But with that in mind, what I would like to do is start our presentation in about a minute or so, just to giving us people some ideas. Now, this is a great workshop, I call it, because it's going to be some hands-on activity as well. This was developed actually for a junior high school project that turned into an exercise to actually demonstrate how the airplane wing and winglets or sharklets do work on that. So with that in mind, if anybody has any initial questions, I'll be happy to answer before we get jumped into the presentation. Okay, I don't have any comments, so we'll switch over to actual presentation. So it's about airplane wing, winglets, and sharklets. So there are different kinds of wings that over the century of the flying, you see that have developed over time. Obviously, the natural wing, of course, the birds, which is where the motivation for Wright brothers and others came along. And if you look at over the time, is on the bottom right that you see the I think Brilliant plane, which was the first one to. Let me turn my oops. And let me turn my laser pointer. This is the first one to cross the English Channel in about 1909, 1910. which is a mid wing level. Some more different variations of those things, and the biplanes and the triplanes. The most famous triplane you remember is from Red Baron. And so what it was, the Red Baron essentially was a very good pilot, obviously, but he understood the the dynamics of the airplane or flying, where having his triple deck wings allowed him to climb higher. He did not have essentially any faster plane or anything, but he could climb higher than others because of the lift. And then he will actually, from the high above, he will see all the enemy fighters, and he will dive, and that will give him an extra speed that allowed him to maneuver. So again, this is over the years things have evolved, and I'll go into some newer wings and everything, but they do exist all around us. So what does airplane makes fly, right? And we have heard about all these four forces of flight. The truth is, what makes airplane fly is money to maintain the airplane, or gasoline and all that thing. But that's just a side joke. Every instructor would ask you in the beginning of your flight training if you're going through that part. But when you have these four forces, lift, and the gravity of the earth, thrust, and the drag, when they are all four at balance, you are airborne, and you need to have a higher thrust, so you are moving forward, and the lift that allows you to fight the gravity and stay at the particular altitude. So again, so when you have a lift is higher than the weight or the gravity, you're going to rise, your plane is going to rise. When you have a higher thrust than the drag, it's going to be, the plane would accelerate. So classical four forces that, that exist. Now, okay. I think so. Sorry about that. So over the years, again, the wings has evolved. We talked about the, biplane and triplane or triple decker plane. And then when you looked at the fighters, the two at the bottom one, you can see that is classical wings that you see it, and a delta wing, this is called. In case of fighter, initially when they're just climbing through, they need a greater lift, and you see that the wing forward, and then they pull the wing back, or called a swept wing, in the mid-flight, which is when they need to reduce their drag and use that energy for the speed. So as you see on a lot of these swept wing fighters, they're called, they would climb as a regular with the wings spread out, a greater surface area, allow them to climb. And then once they are in a combat mode, they pull the swept wings backwards, or delta wings, and allows them to pick up a speed, which is what essential for any plane. So again, it's a balancing all your four forces. And when you look at that, how wing provides the lift, you can see that a classical, we talked about Bernoulli principles and everything, but when the wing, when the air is passing through the wing on the left side here of the picture here, the fast moving air is going over the wing, and there's a less pressure, versus the slower moving air at the bottom has a higher pressure. And as you know, that from higher pressure to lower pressure, always the equilibrium moves towards in terms of balance. So that provides you the lift. And of course, the chord line we talk about, which is what the imaginary line from the leading edge of the wing all the way to the tail. So when the angle of that wing or the camber is changed, let's say you climbing, the front is going to be lifted. So wing has to, the air has to move faster on top of the wing, creating a lot less pressure than one below. That allows you to lift. When you are descending, your camber leading edge is going to be lower. Now you have reduced the fast moving air speed, and hence the lift is less. So you are using basically angle on the wing chord to manage your lift. this is assuming that we are not changing a lot of power changes. Okay, that's very simple. I know some of you are pilots, and then we do have to always manage the power, but that's a separate thing. Right now, we're just talking about the how wings works, how it does provide the lift and so forth. Now, there's a lot of the aspects of the how wings works and all that is basically Newton's second and third law of motion. So in terms of the net force on an object is always equal to the rate of its momentum change, and every action is equal and has an opposite reaction. So classical Newtonian laws second and third. Now, this is from the NASA's lab, and they actually define as to how the forces are working when you are using the vector thrust. Means you are using that force to go fast forward, which is converting to the speed, versus when you are in climb. And this is what basically on the second slide I talked about, that you are changing the camber, the angle on your wing to allow you to climb, give you a greater lift and be able to climb. Once you are into a climb and then you are on a regular cruise mode, your camber changes, and now all of a sudden all that thrust is put into work towards the speed. You can try to play around with these equations if you want to design an aeroplane or even experimental plane. And this is not just the only couple of slides it will allow you to design a plane, but just to give you an idea, there is a science behind it. And obviously, when you have all four forces, the vertical axis and the horizontal axis with the flight path are balanced, that is your center of gravity. And why this is important is weight and balance. When we are taking off, sometimes we have cadets or we have seniors during the mission, or as a AOBD, I'm asking for the weight of the crew because only certain amount of weight can be carried, and then we have to look at that. Maybe that senior member cannot be in the front seat because our center of gravity is going to affect the flight characteristics, and maybe that's why he's not the right person for this mission or this particular sortie, and we kind of have to play around with those things. So that things goes into the whole what you see here about how the forces of flight affect. Now, in terms of all these four forces that we talked about, and the fighters, which basically is the speed is life. Of course, that famous quote was used in a Top Gun, but you talk to any fighter pilot before Top Gun, they would tell you speed is life, and that's because of the combat is a different scenario than when you are in a commercial space, commercial flight or a GA. To give you an idea about the commercial, here is a particular aeroplane, commercial plane, to just picture of that. When it's flying through the space, that wingtips allows us to generate vortices, and that vortices actually affects the airflow going over the wing, and now it's no longer, lift is as great. Because remember, the air over the wing has to go faster to create a low pressure. When these vortices are generated and interrupts that flow, you're not getting as much efficiency as you would like to do that. So what over the years, the design implementation or airplane designer found that when they introduce a little winglet, it's no longer vortices are created and rotated around the wing or tip of the wing and affecting the airflow, but actually it kind of like it slices through. So you may have seen some famous pictures where the jet plane flying through the clouds and the semicircle vortices are generated right behind that, and it's behind the wing airflow rather than at the wing flow. And that is the whole idea, is that now you are continue to gain that efficiency that you have generated with the wing vortices. Why that is important in commercial plane is now you have a greater lift, so that means you're not fighting for the airspeed like a fighter is needed, but in commercial you got a greater lift, so that means your fuel efficiency goes up. You're burning less fuel trying to keep the plane afloat in terms of that, assuming your airspeed is not changing. What does that mean is because of the efficiency, lower cost, you can carry more weight and so forth. So this is the key thing about the commercial flying on winglets, how that affects. So over the years, the winglets have changed. And to give you an idea, here is a classical picture of two different kind of winglets. This is a 737. Boeing uses this kind of winglets, and this one is basically a blended, you see a small one. This is the Airbus Airbus airplane design, and this is how it looks like in the air. Okay, so the basic intended effect of introducing either one of these winglet or sharklet is going to be to reduce the aeroplane's drag. Drag is reduced, you get more forward speed. In commercial plane, you're not fighting as much for airspeed, so you actually gaining your efficiency, fuel efficiency or the lift efficiency. Okay, oops. So here is a real world example from Boeing itself, and this comes from the Boeing website. So when you have a standard commercial plane, you see that over here, and what you saw, the wing lift area, graphical representation. When they introduced a winglet, it's like a 737 style winglet, they saw about 8% improvement in their efficiency of the wing. Okay, when they introduced this blended, which is called AT winglet now, you see that it's kind of a mixture of those two. This is one of the semi-newest one, or the second newest one. When they added that portion to that winglet, they got another 1.5% or so of efficiency into the fuel. So overall, going from this top wing design to the bottom wing design, they got roughly 10% of fuel efficiency. That doesn't sound like as much, but if you think about it, you are flying a 15-hour flight across and burning, thousands of gallons. 10% fuel is a lot more deal, and now you're carrying 10% less fuel because of the efficiency. You can carry 10% of more cargo or passengers. That generates a revenue. So that brings the efficiency aspects of the winglet or the sharklets, as we talk about. Again, this has been a great improvement, in the commercial airline. So how does it affect? Well, it's showing up in general aviations too, as people are finding the, importance of it. So one of the things with in the commercial, GA, is not only efficiency, but also the stability it generates, because you're not fighting the vortices anymore. So you have a lot more stability in the turbulent air we are flying through. So here is one of the European small GA aircraft, two-seater. I forgot the model name, but you see that they have the winglets, but they're not all the way at the end. That is slightly off of that. And again, that has to be designed and kind of tested. Here is a very unique one that you can see in the GA jet. It's almost like a U shape. Okay, I have never seen in other airplane, but this is one of those, and that's why I wanted to point out is that all winglets and sharklets, there is also some differences in that aspects. It's a twin beach, and you can see the nice winglets have been added on. This is a much later on addition, so that was a STC most likely by the FAA to be able to add these winglets to that. Again, commercial here, you see the nice new generations of the planes coming through here. Not only the wing has a winglet, but on the tail you can see the rudder if you can see that, is also acting more like a winglet. And it's almost like a F-14 or F-15 tail with a V shape or U shape type of rudder that allows us to efficiency in a commercial jet. This is one of the most latest one that Airbus concept plane, they are working on it. If you look at that, again, to reduce the drag is the whole idea to increase the lift. This almost looks like a B1, B2, B1 bomber, sorry, B2 bomber, excuse me, with a couple of jet engines on the top. Again, this is at this point is a concept plane, but we may be seeing it in the near future. So again, the Winglets has improved the fuel efficiency and hence, making it more sustainable or economical aspects for the airplane in commercial stage, and it's also slowly coming into GA, especially for existing airplane. The ISTC, FAA requirements and all those things are a long process, but we may see that more frequently. So with that, what I would like to suggest is, this is great, but can we do something about it? And again, this is a workshop that I held at one of the spring encampment to demonstrate that how Winglets actually works, and is a AEX. It's about a 1.5 hour to 2 hour event that you all AEOs, you can do it on a Tuesday or Wednesday night, your meeting night, be able to also earn your AEX activity for these things. So if you want to go, and I'll give you about a minute or two, get 4 or 5 different paper from the printer, or even if you have a sitting newspaper or something next to it, that would work too. And I would like to switch to camera, Lieutenant, if it's possible. Lieutenant?
Major, the camera is on right now.
Okay, great. Thank you very much. So we're going to build an airplane, and here is something that you will need. Now, these slides are available, the workshop purpose one, are specifically available on our website, Wing AEX conference website. So you can take this, you can work with these things and build it one yourself. So very simple requirement for this: get a standard printer paper. Everyone has it around handing, or even like in my case, I grabbed some which was like we had printed it, but when we don't use it, either we shred it or something like that, or you use it as a scrap paper. You can use those things. There are 11 by 14 and 11 by 17 size papers. That works very well too. And I'll talk about that in a second about how this all works. But as a first round, I would suggest try with 8.5 by 11. This works great. You can use any craft paper or a brown grocery bag paper. And of course, those papers are heavier. And then again comes to weight and balance to stay up in the lift, and to provide enough lift in the flight is crucial thing. So that's a separate exercise you can do one evening as a second AEX activity. You can grab scissors. Those are optional. There's not a lot of major cutting or gluing at all is involved in these things, but you can basically cut with your hands. It's very simple. You will require a watch or some sort of timer to record time, a measure tape, so you can measure the distance traveled by your paper airplane. Pen and pencil to record your observations, and finally some sort of graphical program. And most people have Sheets or Google Sheets or Excel or something available. Very simple requirement. Very easy to achieve those things. There is no glue, no staplers, no dangerous things involved. Even the scissors are optional. So let's do. If you are working with me, very first thing is to take the paper and fold it precisely in half. Okay, there's a very key thing, and if you are also looking at those slides yourself, you will see that is you fold it exactly in the half. All right, make a nice crisp like this. Okay, the next step is going to be taking your paper, fold it on the first half, line it up with the first fold. And sorry about that, but here, this is how the first fold is going to look. Make it, the precision is a key in your any of these folds you are going to do. Okay, and the second half would be the second portion of the fold. So now you have a triangle pointed arrow. Okay, again, precision is crucial. And the next step is you're going to fold this in half and use this edge as a folding portion. I'd like to ask if anybody's making online right now with me in parallel. If somebody could respond or write a comment on it, and Lieutenant would be able to, because I cannot see you at this point right now. Okay, so this is what you have folded, and this is most of the airplane we make it is like this. Nothing new about this thing. The next step is slightly different. You fold it inward with follow your original fold, and you will see a rectangle size of your paper, a rectangle right here. Okay, the part which opens up, you're going to go there. Okay, again, this opening up, you're going to cut about 1/2 inch to 3/4 of an inch, like an L shape. Okay, this is where either you can do it with the hand, which is what I demonstrated, or you can use scissors. If you cut too much out, and these are part of the exercises, you can do that. And when you are working with your cadets, you can make multiple planes at the same time, because we are going to test a few things at the same time. So once it's done, okay, this is what it looks like. Then we are going to take this, okay, and fold it backwards. Oh, sorry. This. Okay. One more time. We're going to fold it exactly into here. So here is first half of that fold. You can see that. Okay. And we're gonna fold second time again here. Again, you line up everything very well. Okay, and that there is that little cut area and that little triangle that points out. Okay, so you're gonna fold this over. That actually now locks your entire fold for the aeroplane. The next thing is slightly different than a lot of the books you see in the paper aeroplane. And to me, this one works far better. Is most paper airplane, how to make paper airplane books talks about doing this way. We actually are going to do opposite. We're gonna fold it backwards so that that little triangle is gonna be down there. Again, line up everything precisely before you make a final fold. Very nicely. Okay. And we're gonna do one more. Now we're gonna design a wing. Now, multiple ways to design this wing. You can take this edge right here and line it up with this edge. Do one thing at a time. Okay, and I'm gonna show you in a second. So here it is. That wing we folded, line up with this edge right here. So that, so it's a nice fine line. Now we are going to do this second side and fold it exactly same way, line it up with the wing and the fuselage area. So now you have a nice airplane with symmetry. If it was done precisely, you will see that. Now, when you have this, you want to do a little bit up there so it gives a wing a little lift. This is your airplane. This is that part you put a tab, that little triangle that holds the airplane together. That is a very pretty close to center of gravity you have built for the flight. Okay. Now, if you notice that this is like a delta wing airplane. Okay. I did something else where rather than lining up wing with the fuselage, I had a little amount on the fuselage and I gave a much greater wing surface area. So you can see the differences between the two of them where I increase the surface area here. Everything else is built exactly. And to give you an idea, it's see how much of a surface area we gain. So again, this is another experiment you can do with your cadets where you are playing around with the wing surface area. This is almost like a fighter. Now this is where, you know, when I mentioned about that you want to make 2 or 3 airplanes same time, and this is where it comes in, because you make your control airplane, which is what this is. The second airplane you would be making, you would have made exactly up till this point, same thing. We're going to create a winglet. How do you do that? See that pointed edge on these things? You want to fold it upward if you're going to make it winglet. Make sure that when you do it on the both sides, it's about the same amount of fold you are doing it. Okay. Does it look like a winglet a little bit on a delta wing? Okay. Now, so you will have two paper airplanes, one without the winglet, one with the winglets. I'll share with you in a moment a slide, but where we also tried was folding it downward winglet, kind of a semi winglet sharklet type of scenario. Now, the key thing is using, you know, exact same force with both airplanes. That is a key thing in this process. Now, if you are working in a hangar or higher elevation or something like that, second floor window, it will be kind of nice when you throw it gently. It allows you to have that extra, you know, altitude, so it's a longer time. If not, if you are in a room or on the ground outdoor activity, that works good too. Harder you throw this plane, it doesn't work as well. But key thing is the same amount of force. You want the, you know, wind to blow through, the air to go over the wing above and below. Okay, that's one way to do it. Another one, as I mentioned about, is building this where you have a greater surface area than this one. And then you can test against each one of these as well, saying that one without the winglet like a fighter versus one regular extra surface area. Again, a whole new separate activity, or you can do it in one evening with multiple wings. Also, if you remember the very first fold I did with the triangle, I said, make sure you precisely make that thing. In this case, I'll show you. I purposely built a plane where my first fold was exactly to the point. But the second one, I did not line up with this, gave some extra space here on the head. Okay, what it does and everything else remains same. Now the nose of this airplane is a lot different than this. Again, this is like a fighter, very pointed, sharp, versus this would act like your commercial plane or a different aspect. Again, these are the good things you can play with your cadets, be able to record and they can make an observation and make a STEM activity out of this thing. So again, a lot of different ways. There's another one right here. I kind of gave a little like a Concorde shape. I folded not all the way to the point of pointed part, but slightly before that. So now this is more like call it a Concorde. This one is like a blunt nose. This is like a fighter. You can create 2 pairs of each one of those with the winglets experiment and be able to do that. So how do you do that thing? So if we can switch to our slides, Lieutenant, I would appreciate. From camera to slides.
The slide is on right now.
Okay, good. We are on slide. Okay. Or my desktops, excuse me.
Yes.
Okay. Am I on the, okay.
Apologize.
All right.
Okay, there we go.
There you go. Okay, so good. So we are on slide. So this is again what I walked through. These slides are available on the Wing website. Here is a paper pointing them, folding them exactly, lined up with the two edges. And you get a nice first fold. Right here we're talking about. Of course, the second step is that folding. Once that nice crease you have, you're going to make a pointed triangle by again lining up this two different folds exactly to the point, again pointing it out to that they have to line up exactly. And then the next step is that once you made that triangle arrowhead, you're going to fold precisely at this same right here and point it out here that how that matches up. Okay. Once it's done, that as I pointed out, you fold these things inwards and you cut out a small piece. The L shape here gives you an idea with my finger against the cut we have made. You can play around with that cut because more you cut out, the less weight you have, but your center of gravity should remain about the same place. And that is the key for this whole flight aspects of it. Once that is done, that triangle was cut out, you're folding one more time. And this is that cutout that I pointed out here. And then you're going to take this tab, fold it over right here as shown here. Once it's done, here is that fold over tab. You're going to fold the plane backwards. As I said, this is slightly different than the paper airplane books. You see that thing, which is, to me, this is a much better design, but that's my opinion. What it allows you to do now is you have a nice pointed things and you can create the different wing surfaces. This is the one where I pointed out that this edge was lined up with this part of the fuselage and the same thing on the other side. So that kind of looks like a pointed or fighter type of a delta wing fighter. When they are all folded out, this is what your plane looks like. This is your center of gravity, that folded point. Works pretty well overall. And here we go. We're folding the edges of those airplane. Try to fold it exactly same way. In this case, you can see that I folded upward. And in this case, I folded downward. So you can again create a winglet, sharklet type of design right here.
Major, we have a question on the area.
Go ahead.
Could you repeat how to achieve the different wingspans? This is from Second Lieutenant Amol Bargia. I'm sorry if I misspoken your name.
Okay. So how to increase the surface area? You mentioned that. Is that the question?
Could you repeat how you achieve the different wingspans?
Okay, so that's very good. Let me go back to my previous slide. Okay. So this one is which is where this area was lined up with this part of the fuselage. Okay, you see how much the area is here? You got a lot more area here, the height wise fuselage part, right? If you actually fold over more, okay, and can we switch to camera? So I think it's probably easy to demonstrate or show it. Let me know when I'm on camera.
Your camera is on right now.
Great. So this is the one I mentioned about that when you fold over and line up exactly with the fuselage right here, this is a smaller surface area, okay, which is what is shown in that. In order to make a larger surface area, say that once it was like this, I folded a lot more area, okay, and there's a lot less fuselage compared to this plane. If I can point it sideways, you can see that. So it was folded a lot more. Once I fold my one wing, then I turn over and I match the second half of the wing exactly same way. So now you have a greater surface area. Again, so it's the last part of the wing. When you're folding it, you can see that how large this area is compared to this one. Almost 3 folds or something like that, 3 times. That's how you increase the surface area. Now, obviously, if you want to make it even, you are into math and your cadets are interested, you can actually calculate the surface area, because now you have a unusual rectangle and you can calculate the length and width and all that from there is surface area. But I know the cadet sits through all day in their math and other classes and they get bored. They may be more, inclined to actually understand the concept, how the surface area is greater just visually and be able to see the difference in the flight. Okay, does that answer your question, or do I need to explain a little more or clarify?
Yes, according to.
Great. All right, so we'll go back to slides again. Okay. So we talked about, upward winglet and the downward winglet or sharklets. So now we test flight. Okay. So take your 2 best planes. Now, if you're doing one of the things, if you have a lot more cadets, like at one of the encampment I did, I have over 100 cadets in the room. So we made the group of 5 to 6 cadets, and each one made the airplane, but they got to choose the best airplane. They had it with winglet and without winglet. Okay, so you can kind of, play it out the way it works. If you are at a squadron level and you have 10 cadets, then it might be better to let them have a competition among themselves and kind of make a, fun activity. And then, as I said, is you're going to measure the performance of the both airplane. Okay, key thing is using the same hand force for each flight. So either you can use both hands and throw it at the same time, or do one at a time, whatever works. But you are going to need the, people measuring the time is a key thing in that flight. So if you're gonna use the same cadet using 2 airplanes at the same time, at least have 2 people with the stopwatch to measure time. Again, measure time in flight in seconds or minutes, depending upon whatever works best. Okay, and then measure the distance. So 25 feet long measuring tape works great to start out with outdoor activity, and measure that thing in inches or feet, depending upon how far the airplane has traveled. And then next, once you collect all the data, you're going to demonstrate the data, how that works. On the y-axis, you would have a distance travel, in inches versus feet, versus on your x-axis would be type of the wing you are using it. You can also plot your time of the flight in seconds on the y-axis, and on the x-axis you will have the type of the wing as well. So you kind of get the conclusions from that. So how does the data look like? So here is a small example of a small group. So here, this is what data was collected. So regular airplane wing, which is what we did it without any winglets or anything. And in this particular case, the airplane traveled 47 inches and it flew for 14 seconds before hitting the ground. So now you can actually calculate the speed of the airplane, how many inches per second. And then if you want to make one more step here to convert into, hours and miles and kilometers and all those things, it will get smaller and smaller, but you get the speed and you can say how fast was your airplane flying. Here is a second aeroplane where which we had a winglet, upward winglet. It travels 62 inches, so compared to 47 to 62, you're about 32%, longer distance travel in this case. And in this case it flew extra second, which is about 7 more seconds. So you can see the difference right here, that it flew longer time-wise and the distance-wise. And the average speed was slightly increased too by reducing the drag. Okay, and that's about 23%. Just again, this was a small sample. If you have a 10 cadets or 50 cadets, you can collect all this data and make a really nice STEM activity out of this thing. Here's a downward winglet where it traveled 58 inches, still more than the without any winglets. And then it flew about 14 seconds, so same amount as the regular airplane. Okay, but the speed was greater, almost same as a winglet upward versus downward. But again, the distance travel is more than without any winglet. That's about 23%. You can demonstrate these things with your cadets on another way of representing data, because sometimes not everybody grasps the numbers or things like that. So here is a regular airplane and winglets upward and downward, or here is the time in flight, and you can see the differences. Okay, so this is a great little exercise. So they learn a little bit about the winglet and how it affects and what they see in the real world, and a little exercise they can you can do as a part of the AEX activity with them for that for one evening of your session or so. Again, if you have more time, you can make a greater surface area and the regular surface area. You can try all those things. So here are some STEM ideas that I'm proposing for AEOs, is to repeat this exercise with weight. So now you can have a standard printer paper versus a craft paper or a brown grocery bag paper, something like that. And the weight is going to be affected. So again, you can demonstrate the weight and balance aspect, and also how the winglets with those weights improves efficiency of the flight. Obviously, the heavier paper, with the heavier plane, so it would travel probably less and the less time in the flight. But with winglet, it would still show the improvement over regular airplane. Change the wing design, and that we talked about is how to get the greater surface area, and that allows you to be able to demonstrate that how commercial planes or the cargo planes, they care more about the lift and be able to carry over speed. They are not in a combat mode, so they do want the more efficiency. Again, another thing is all of these discussions I pointed out, they have to be precise fold. You can actually let them make the mistake and show them when the wings are not equally well folded or the winglets are not evenly folded. Airplane would have a tendency, either if it is a nose heavy, it's going to crash right by their feet, or they would be swirling to the right or the left, depending upon what the asymmetrical wing or the winglet design was. So again, these are the great concepts you can include in this. If you can think of anything else, besides some of the ideas I've proposed here, please let me know. We'll continue to improve those things and share with other people. With that, I'm going to leave my first slide here because that one has my contact information. I am in Illinois 049, which is a Milwaukee squadron. Please feel free to reach out to me, and anything else I can help you with. If you are in Northern Illinois and you want to do this, and if you can coordinate, I may be able to come out and help you with that as well for your AEX activity. So with that, I'm open for any questions. If you can go to camera, that would be great. They can see me rather than, hopefully they have my email address is very standard. Any questions? Any comments, any suggestions?
Major, we are at
Yes.
the top of the hours. We would end the event now.
Okay, so if you have any questions, that is my email address. Please feel free to reach out to me. And I appreciate you guys being here, and hopefully, you can use this activity. It will qualify for STEM as well as for your AEX. And all right, thank you very much for everyone here. Bye.